let me repeat everything that Gil said. Thank you to the organizers for organizing this very inspiring workshop. And also thank you, Gil, for giving a talk that after that my talk is much simpler to give. So when I sat in the talk this week, they were very inspiring, and I realized that there are two types of talks. And the type of talk I should have prepared is the following talk: TCS, global warming, income inequality, and the meaning of life. So that's the talk I should have given, but unfortunately I haven't prepared it. And instead of that, my talk is more like, let epsilon be greater than 0, I is in n, rho in 0, 1, and so on and so forth. And especially before lunch, it's not clear that this is the optimal talk to give, but it's already prepared. So what I'll try to do, I will try to go slow. The talk is more focused. It's more about like really some set of results that are intimately related and have some connection to PCP. And I will try to go slow. I will probably finish early. We don't have to cover everything. And because it's before lunch and I don't want to fall asleep, please ask questions. Okay, so that's what we're going to do. Okay. So I'm going to talk about two notions that were mentioned in Gil's talk, and I'm going to, the two concepts that were mentioned in Gil's talk, and many of you know them. One is noise stability, and the other one is majority function. And I'm going to talk about the relationship between the two. I'm going to talk a little bit about, I think there are some experts in the room, a little bit about all the results from about up to 10 years ago, and a little bit about newer results. And one of the reasons I want to mention the new result is I think the new results might potentially have some applications to PCP, and as all the results had. Okay, so I'm going to start talking about noise stability. So this is going to be, there's going to be a couple of slides of definition, then I'm going to tell you some stories, so don't fade out quite yet. You can fade out in a few minutes. This is noise stability. This is the definition of the basic concept that we're going to study. So we are going to be in Gil setup. We are going to look at bit strings that are chosen uniformly from 0, 1 to the n, which for me are -1, 1 to the n. And I want these bit strings to be correlated. So for each I independently, the probability that xi is equal to yi is going to be a number bigger than a half. I'm going to parameterize how bigger this number by half by rho. So it's going to be 1 plus rho over 2. Each one of them is individually uniform, and the probability that they're equal is 1 plus rho over 2. So one way of thinking about it, thank you, Boaz, for asking a question. You first of all choose x. You choose x uniformly at random. Then for each I independently, you decide if y is equal to x or re-randomize. So you choose it to be equal to x with probability rho, and you re-randomize it otherwise. Okay, so that's one way to think about it. This is definition. And the discrete noise stability of A is just the probability that both x and y are in A. So Gil mentioned that this is an isoperimetric quantity. Why is it an isoperimetric quantity? One way to think about it is, okay, I don't have a way to draw anything, but here's my set A. Here's my point x that happened to land in A. Now I'm going to have the set y. The set y is not just a random point. It's a point that's correlated with the set x. Right? So the question if y also lands in the set x, in the set A, or it lands outside, somehow related to the structure or the boundary of the set A. Okay, so that's the reason it's an isoperimetric question. And since the Gaussian measure wasn't mentioned a lot in this workshop, let me mention the Gaussian version of this problem, because this will also come up. So it turns out that it's very useful even to study the discrete noise stability question, to talk about the Gaussian noise stability question. What's the Gaussian noise stability question? We're doing the same kind of scenario, but in Rn. What's the measure in Rn? The measure in Rn is the standard Gaussian measure in Rn, meaning we have n coordinates. Each of them is independent standard Gaussian. What are we going to do? We are going to choose a vector x that's chosen from this standard Gaussian measure. So you think about it as laying on some high-dimensional sphere approximately. Then we're going to choose vector y that's correlated with this. So the way to think about it geometrically, more or less approximately, is that the inner product between x and y is going to be rho, okay, under the right normalization. And then we can ask the same question. We can define the same concept. The stability of a set F in Rn under this distribution is the probability that both n and m lie in F. Okay, so this is a terrible slide before lunch, but I made this just for those of you who want to take a nap, So now what you have to take from this slide, so there's a definition here, but we want to say what are noise stable sets and what are noise sensitive sets. So noise stable sets are sets for which the probability that both x and y lie in A is strictly bigger by epsilon, by this epsilon, than the probability that x lies in A times the probability that y lies in A. Okay, so what's the way to think about it? If my if my set is sort of dust, it's dust everywhere, right? So it's like little pieces everywhere. It's like a parity in the discrete cube. You can really think about dust in Rn. Then I pick X and I tell you that it's A. It doesn't tell you any information about the fact that Y is in A or not. And therefore, the difference between the probability that X is in A and Y is in A minus the probability that of A squared, then this is just going to be close to 0 or approximately 0. And so this should be a minus sign. If the stability of AN minus P squared, the probability of AN squared goes to 0, then we say that AN is noise sensitive. Okay, so noise stable means that if I tell you that X is in A, you also learn that it's somewhat likely that Y is in A. Noise sensitive says that if I tell you that X is in A, you say, did I learn anything about Y? No, you didn't learn anything about Y. Okay. Question over there? Feel free to ask. Right, so very good question. So for those of you who know about coding theory, you say, why is it telling us this story? You know, you're just telling us about binary symmetric channel. We all know about binary symmetric channel. Why are you telling us this story over again? So the main difference between coding theory and the perspective that we're taking here is in coding theory, you take a very, very small subset of minus 1, 1 to the n. And these are going to be your code words. And then you ask about decoding, which is to say, given Y, can I guess which X was I coming from? In this setting, the noise is the same noise, but the sets are much bigger. You would think about sets that's not exponentially small in minus 1 to the n. It's going to actually have a positive fraction of the measure, either in minus 1 to the n or in the Gaussian space. Okay? So it's the same noise operation, but you don't have this ability to say, I'm going to choose this tiny, tiny tailored set where points are far from each other, and therefore I'll be able to decode. Okay, so that's the difference. Very good question. Okay, so even though we like noise-stable set, we should know that noise-stable sets are rare. In particular, if you look at a random function is noise-sensitive. It is, in fact, very noise-sensitive, right? So random functions are noise-sensitive. So you know the noise-stable sets or noise-stable functions are pretty rare. And there are other functions that are very structures, not random, which are also noise-sensitive. So maybe the easiest example is the parities. If you look at bigger and bigger parities, they are going to be noise-sensitive. If you look at critical percolation on the n by n grid, so this is a model that Gil described from statistical physics, this is also noise-sensitive. If you look at the recursive majority function, which is, you know, how many of you have seen the recursive majority function? Raise your left hand. Okay, so many of you have seen the recursive majority function. If you've seen the recursive majority function, this function is also noise-sensitive. So there are many, many functions that are noise-sensitive, but we are going to be interested in noise-stable functions, which consist a very, very small fraction of the set of all Boolean functions. Okay, so why noise stability? We mentioned percolation. Gil mentioned percolation. One application of noise stability that actually Gil, and you know, the 3 dots means that there are many works after that, right? I was just mentioning the first work that I know in each area. Gil actually came up with, you know, a very nice application of noise stability in the context of social choice, which is very confusing. The value of rho there, the correlation, is actually not positive. It's minus 1/3. It's very important that it's minus 1/3. This comes up in the analysis of Arrow theorem, and it was used a lot after that. It has to do with communication complexity and the problem of correlation distillation. This is related to somewhat interpolating to problems in coding theory. And I guess the reason I'm talking about this here is that it's related to hardness of approximation in PCP. Okay, so it's related to hardness of approximation in PCP. One place where, so I'm not going to tell you the PCP story because it was told before and it's somewhat a complex story, but one place where it plays a role is that it plays a role as an inner verifier in 2-query PCPs, the one that were introduced in code in his unique game conjecture, where often what you do, the way you choose the X and Y is by some noise, either the noise I describe or some related noise to this noise. And maybe it could be a tool that's used in some ways for unique games conjecture. So there was this construction of Kotter and Moskowitz. I mean, I think the more successful attempt by Muli, Dor, and collaborators, you know, might also play a role using some notions of noise stability. Okay, so that's the reason we're talking about it here. Questions? Okay. And philosophically, as Gil mentioned, you know, in many situations, if you believe your input come with a noise that's the noise that you flip each coordinate independently with some small probability, you are only interested in noise-stable functions because all other functions compute something that's irrelevant, that it's going to be noisy and you're going to learn nothing about this. Okay, So here are some examples. These are my best attempt at graphics, which I borrowed for some previous slides. So just to set up in a place where we know what's happened. So now I'm going to, before I talked about the definition of noise stability. Now I'm going to give you some canonical example of noise stable functions. So all of these functions are Boolean functions that are actually noise stable. So the most stable function ever is the dictator function. Okay, this is actually an easy theorem that the most stable function is the most stable balanced function is the dictator function. And the way you can do it, you can see it easily from the definition. It's you have this 1/4 plus rho. This rho is the reason that you have this noise stability. The majority function, which is also going to play an important role here. So the majority function, all of you know, but let's just say what it is. The majority, you just count if you have more +1 than -1. If there are more +1s, you're going to say 1. Otherwise, you're going to say -1. The stability of this function, you can write a formula for, and the asymptotics of these formulas n goes to infinity. You get, again, 1/4 plus something positive. This something positive is arc sine rho over 2 pi. And while this might seem like an interesting calculation, it actually relates to, or it actually comes from the fact that if you look at the Gaussian noise stability, and you look at the noise stability of a half space is just all the points, say, on the left side of a half space that goes through the origin, then the stability of the half space is going to be exactly the same formula. Question over there in the back? No, you're good? Okay. Good. Okay. So that's some examples of some sets that are noise stable. Gil already mentions the notion of influence. This is going to come in a little bit, so let's take an aside about the notion of influence. So the influence of a set, or for a set, the influence of the ith variable is the probability that if I change the variable value of xi, it's going to change the answer to the question, is x in my set or not? So this is a different isoperimetric question. The isoperimetric question of noise stability is sort of global. I choose x, I choose y. X and y are different in a linear number of coordinates, and I ask what's the relationship between x is in A and y is in A. The notion of influence is a more local notion. I choose x, I change the I coordinate, and I ask, does this change the answer to the question, is x is in A or not? So some examples that's good to have in mind. So our two noise stable functions before have very different influences. The influences of majority, all of the influences of all the variables are about 1 over square root n. It's easy to see. And for dictator, the influences of dictator itself is 1, and all the other influences are 0. Good? Okay? Okay, so let's talk about the other players, which you all know, but let me just put this definition anyway. So I'm just going to talk about majorities that are balanced. So I'm going to look at f of x, which is the sign of the sum of wixi. Then we call f of a majority function or a threshold function. Again, my xi's are plus minus 1. I'm always going to assume that there are no zeros. So I'm not going to worry about zeros. So I assume that the sum of the wixi is never 0. And the simple majority is the function that we've seen before. It's just all of the weights are 1. Okay, so, and we know that dictator is also a majority function. It's just one weight that is 1, and all the other ones are 0. Okay, so now what I'm going to talk about now is, all I want to tell you today is a small story about the relationship between majorities and noise stability. And I'm going to tell you 2 or 3 results about majorities and noise stability. Then I'm going to tell you some progress that we can make from this result, and then some open problems. That's going to be the story. And then a proof or lunch. What do you prefer, a proof or to eat lunch? Okay. There is a proof, so we'll see. Okay, so the first result is that was proved in this paper by Benjamini, Kalai, and Sham, is that all majority functions are noise stable. So if you look at the set of all majority functions, together they are all noise stable. Okay, so this was proved with some exponent in the paper of Benjamini, Kalai, and Sham, and it was improved, the exponent was improved to the optimal exponent by Yuval Perez, and then there are other improvements of these two polynomial threshold functions. Question? Okay, so these results are actually stated in terms of noise sensitivity. So one thing that I'm intentionally not talking about is how things depend on rho. Okay? So when rho approaches 0, you can ask what's happened as rho approaches 0 to the probability that you go inside or outside of the set. And this exponent is the exponent of the noise sensitivity that was studied in this work, but it's not super relevant to this talk. Thanks. Okay, so one result is that the exponent in this setup, which we did not define, is 1/2, and this is proven by this result in Yuval Perez. Right? So that's nice, one nice thing, right? So we want to understand the very small set of noise stable function. We also know that the set of majority function is very small. There's a result by Hastad that enumerates all majority functions. There's a very, very small number of majority functions if you want to know how many are there. So we know there's this small set and there's this small set. One small set is contained in the other small set, right? So the set of all majority functions are noise stable. Second, for monotone functions, there's an inverse. So this inverse is related to this list decoding question that Boaz presented in his talk. So let me state the result. So we have a set of monotone functions. Some monotone functions are not noise stable, like the recursive majority function. But if you have a set of monotone functions and you want to know if they're noise stable or not, it's enough for you to ask, are they all correlated with majority functions? Or the quantitative way to think about it is you want to know, do I have positive noise stability, strictly positive or bounded away from zero noise stability? This is if and only if my function has positive bounded away from zero correlation with a majority function. Okay, so we have these two small set of functions, the noise stable functions and the majority function. All the majority functions are noise stable, and every noise stable function is correlated with the majority function. Okay, so this gives us a very nice picture, at least for the monotone functions. For the non-monotone functions, at this point, we don't know what the answer is. So like I said, this is, in some sense, list decoding for monotone functions. So for monotone function, you know that if you are noise stable, you are correlated with the majority function. We're good? Okay? I think there's going to be one more slide with result, and then I'm going to ask some questions. The other interesting thing is this expression that we've seen before, 1/4 plus arc sine rho over 2 pi, is in fact not just a random number, it's an extreme number. So in what sense is this number extreme? It's extreme in the sense that if I look at any partition of Rn to two sets, each of them of Gaussian measure 1/2, the most stable partition of Rn into two sets is given by a half space. Okay? There's no partition of Rn that's more stable than this partition. This is the most stable partition. And the result that's derived from that is, so this result is due to Borell. The result that's derived from that with O'Donnell and Loshkevitz is that, okay, so this is a lot of quantifiers. So let's say what it is. If we look at the discrete cube, and we look at the set of measure 1/2, and if all of the influences of the set are less than tau, where tau is some small number, then the stability of the set is less than this expression, 1/4 plus arc sine rho over 2 pi plus epsilon, where epsilon goes to 0 as tau goes to 0. Okay? So these two results are saying that in the Gaussian space, it's very neat. In the Gaussian space, half space is just the most stable, absolutely. In the discrete space, we know that the most stable function is dictator. But if you say, I don't like dictator, it's just one coordinate, it's not really a function. I want a function that's really a function of all the coordinates. So what is a function that's really a function of all the coordinates? Function of really a function of all of the coordinates, one of the definitions that you can come up with is that all of the influences are small. So if all of the influences are small, you cannot get much more stable than majority. As the influences goes to 0, the stability cannot get much bigger than this. And this result, the second result the second result, and its proof played some role in the PCP and applications of the PCP. So like I said, this result and other applications of the invariance principle, this was used in the MaxCut paper with Subash and Guy and Ryan O'Donnell. And then the way it was proved using the invariance principle was used by Raghavendra in order to sort of give this ultimate program that solves all CSP problems optimally, right? So this somehow lies in the background there as the inner verifier. Okay. So let's see, okay, so this sort of summarizes what some of us knew about 10 years ago, and I want to give you some update on the small progress that we made in the last 10 years. So first question that we want to ask, there was this very nice characterization of noise stability of monotone functions in terms of majority, right? So we understood, noise stable, all majorities are noise stable function. If you are monotone and noise stable, you are correlated with majority. Do you have a result like that for non-monotone functions? For functions that are non-monotone, this is a very natural question in terms of sort of this list decoding. The second question is the following question. So we all like influences a lot, but even when the majorities question was arised, and when we wrote this paper about majority stablest, it's natural to ask, do you really need all the influences to be small, or is it enough to have a weaker condition? And a weaker condition that appears in many areas in math is just to have all of some Fourier norm small. In particular, if all of the Fourier coefficients are small, do you still have results like majority is Stablest? So that's another very natural result. Question, sorry. And another very natural question is there a stable or robust version of majority is Stablest? So what do I mean by that? If you are almost as stable as majority, does it mean that you look like majority? Okay, so this relates again in Borell's talks. He talks about robustness. This is the kind of robustness that you want to say. I'm almost as stable as majority, therefore I am some sort of majority. And maybe the last question that I'm going to discuss is that this theory can be extended to other domains. I'm not sure that just product spaces are the most interesting domains. You can look at, instead of 1, -1, 1 to then, you can look at 1 to 3 to then, but maybe you want to look at the Grassmann graph, you want to look at other graphs and ask, can this theory be extended somehow?
When you say almost majority, the truth table is going to?
So we'll talk about, you'll see what we know. So obviously it's not almost majority. Okay, so let's do, good. So Doritis asked a good question. So, I have majority on n bits, and now maybe I have majority on the first n over 2 bits. It's kind of clear that it's almost as stable as the other majority. So that's not quite the right question to ask, right? So there is some freedom in the choice of the parameters of majorities, and what you want to be is you want to close to some majority function with small influences. Good. Are these questions clear? Good. Okay, so let me tell you. So I'm just going to give you the theorems, and then we'll have to decide if to go to lunch or to see proofs. Maybe we'll see some proofs. Okay. So let me first of all start with this question about stability and majorities. So now we are looking at the non-monotone sets. Before we looked at monotone sets, for monotone sets we saw that you are stable if and only if you are correlated with majority. Now we're looking at general sets. So the collection of set AN is noise stable. So this is joint work with John Niemann. If and only if, for some epsilon greater than 0 and rho between 0 and 1, for all n, the following beautiful expression holds. So what is the following beautiful expression? What are we going to look at? We are going to look at the maximum correlation between all majorities and RAN. Instead of AN, we are looking at RAN. We want this maximum correlation to be bigger than epsilon, this probability bigger than epsilon, where we have this RAN. What is this RAN? RAN is a random restriction of rho fraction of the coordinates. This is the same rho that we have on the top. And it's not the same rho of the noise stability. It's actually one of the very good question, Boaz. In all of this question of noise stability, the actual value of rho doesn't matter. If something holds for one rho, it also holds for other values of rho.
Okay, so the definition of being noise stable is independent of the rho.
Right, so one thing that I try to swipe under the carpet, but I forgot that you are here, is the definition of noise stability actually does not depend on rho. This is already in the BKS paper. It does not depend on rho. Okay? So this rho can change value somehow from one definition to the next. But what this theorem is saying, it's not the case that you're stable if and only if you are correlated with a majority. You're stable if and only if when you look at the random function, or what do you do in this random function? In this random function, for each coordinate, you fix it to either 1 or -1 with probability half, with probability rho, and otherwise you let it be free. So you look at random function of 1 minus rho fraction of the coordinates, where all the other coordinates are fixed, and this function will have positive correlation with majority with positive probability. And this is an if and only if statement. The new functions don't have to be balanced. But the original function also, A and D do not have to be balanced.
So just to make sure that the experiment, you first restrict the function, then you find the majority.
Exactly.
After you restrict.
Exactly. So the order is important. First you restrict the function, and then you choose the majority after you restricted the function. And let me make some comments. A similar result shown in Gaussian space. And the random restrictions are necessary, and it's easy to see in the Gaussian space. So one example in Gaussian space that's noise stable is the ball. So if you look at the ball in Gaussian space of measure 1/2, you can compute, and it is noise stable. Now the ball in Gaussian space, it somehow cannot be correlated with any half space, because if it's correlated with, if it's correlated with this half space, there are going to be n orthogonal half spaces that it's going to be correlated with, and it cannot be correlated with n orthogonal half spaces, right? It also answers your question, right? Because when I randomly restrict, I will get a random half space that will be different for different random restrictions. Okay? So that's really the phenomena here. The phenomena here is that you're not correlated with majority function. You are correlated with, after random restriction, you are correlated with. After you restrict the ball, you get a ball that's sort of shifted, and then because it's shifted, it's correlated with the direction that you shifted it in.
On these coordinates in which you
shifted.
So then M is what?
So M is like before the set of all majority functions.
So when you say all majority, you mean still positive weights?
Here I mean all weights.
Both positive and negative.
And also before I meant all weights. And again, I don't think we answered any result. We answered the original question of Kot and Moshkovitz, but we started thinking about this because of this construction PCP related by Kot and Moshkovitz. They wanted to prove some noise stability of some very, very complicated construction. And then Joe and I told, we can't even prove noise stability of this. So let's think about that for a while, and that's where we stopped, right? So it's not that we solve what they want, but it says, I think, actually something negative about the construction that they wanted for the PCP. Because we need this random restriction, it says something negative. This is the only characterization I know for general functions.
Because maybe you want something more explicit. It does not have to do with random restrictions of the same.
Okay, so first of all, of course, there are many, many other characterizations of noise stability in terms of the Fourier spectrum and so on and so forth. But in terms of majority, right, I'm just talking here about the interplay between majority and noise stability. In terms of the interplay between majority and noise stability, that's the only result that we know. Okay, and again, the example in Gaussian space is the ball, and it's very easy to make this example Boolean. Because you do the usual trick that you do of going from Gaussian to Boolean. You have square root n coordinates. Each of the square root coordinates you expand to x1 plus 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 x square root n over square root of n, and then you get the same result in the Boolean space. So you have an example. You have to do the random restriction, and as Boaz asked, each time you get a really different list. It's not that you're going to get the same half space over and over again under different restrictions. So one of the consequences of that we thought about, this result does not imply your result for monotone functions. Okay, so somehow the interplay between the result is not clear. It does not imply also.
But the ball is a majority-like function in some sense.
Yeah, it's a polynomial threshold function of degree 2, right? So yeah, it's a very close to majority.
So is that like something you can prove, or is that like obvious? That low degree, if you replace being a majority.
Right, so one of the results that follow up on BKS and the result of Yuval Perez is by the usual suspect. I don't remember the name, sorry, I'm on the video. Ryan and Rocco, the diagonalists, and so on and so forth, is that polynomial threshold functions are also noise stable.
No, and also the other thing, if you wanted the characterization and allow yourself to use a higher degree than one polynomial, would that then...
This is easy. Yeah, it's easy to prove that if your function is noise stable, then it's correlated with polynomial threshold function. Yeah. This is very direct. Yeah.
Is this result right?
The dependency on epsilon and rho, I believe not, right? I believe that this is not right. And I think the same is true for the original BKS paper. The parameters are not optimized. Good, excellent question.
Can I also add something?
Yeah.
So there's this classic question in complexity theory, maybe it was solved yet, I wasn't around, whether majorities in ACC 06, right? Whether majority can be computed by bounded depth circuits that compute some modulo 3, some modulo 6, and the ends and all.
Yeah.
Is this maybe because majority is noise stable, as we've said?
Yeah.
Is it maybe possible to prove that by proving that ACC 06 doesn't have the property?
Right. So that's a very good question. So I mean, I can speculate together with you. I don't know if it was proven or not. But one of the tools in proving circuit lower bounds is using some version of noise stability, but it's usually together with random restrictions. So, you know, it might play a role, but I don't see a direct way, right? When Hastad proved this law, something like that is going in the background, but it's not the only thing that's going on, right? There's the switching lemma, there's the random restrictions, and so on and so forth, right? So, yeah.
ACC6 is wide open.
Wide open.
You know, I think if anything, you would want maybe some function that is not noise stable under any possible restriction or something like that.
Right, so I thought about it, but for instance, it's very easy to compute parity in TC0. I mean, there's issues. That when you start thinking about these things more seriously, you see that the connection is not very direct, right? So you have to have more ingredient than just using the noise stability. Okay, so the other answer, the next question was, can we prove majority is stablest under small Fourier coefficients? And the resounding answer to this is yes, and it's easy. And it's so easy that O'Donnell, Servideo, Tan, and Wan proved it in 2010 and decided not to write it down. Then Jones wrote it down in 2016. And OK, I actually thought it's interesting, so I did write it down, and I actually made it a little more general, a little stronger. But the statement of the majority stablest is to even just underlaw Fourier coefficients. So the same setup. Now, instead of the condition that we have low influences, we have this condition that the L infinity norm of the Fourier coefficient, except for the empty set, is less than tau. Then still the statement of majority stablest holds. So you don't actually need low influence. It's enough that all of the Fourier coefficients are small, and you get exactly the same result. Like I said, I have stronger and more general results in my paper, but both the proofs that I did and the proofs that in OSTW or in Jones, both use regularity lemma. And at least in terms of the mathematics and the last slides in Gill-Stokes, it's interesting that by using tools from additive combinatorics, by using some regularity lemma, and combining with the analytic tools that we know in discrete Fourier analysis, you get a stronger result that we didn't know before. The proof is not hard, so. So it's a different regularity. It's not the standard regularity lemma that you know, but essentially, OK, so for Noga, I'll tell the proof to Noga in 1 minute. Whoever catches it up in 1 minute, you know, OK? So the proof is the following. What you do is you build a decision tree, and you build the decision tree in a way that all the leaves have low influences. Now, your energy, so you have to be a little careful because you don't know that the sum of the influences is small, so you first apply a little bit of noise, and then you know that the sum of the influences is small. That's my proof, but their proof is related. Then you know that the sum of the influences is small, smaller than a constant, and that's going to be your energy function. Your energy function is going to be the sum of the influences, and then you're just going to have a decision tree, and in all the leaves you're going to have functions that have low influences. The fact that all of the, where are you using the fact that all of the Fourier coefficients are small? You use the fact that all of the Fourier coefficients are small in concluding that in each of the leaves you didn't change the value of the expected value of the function by much. Because you just condition on a small number of variables, since you condition on a small number of variables, and then you just continue from there. Okay, so that's basically the proof, right? So there's an energy function, you work with this energy function, you get some regular structure. Here is at most leaves of the tree, and then you go from there. Good. Okay, so this is you can do it in 1 minute for Noga, which says something, right? You know, something you need 5 minutes for Noga. Okay, so that's a second positive answer. This is the ugliest slide. Okay, maybe. Okay, so we also have a positive answer for the third question. We have a stable version or robust version of majority is stablest. What's written here in the first half of the slide is the previous statement that we had for majority is stablest, so don't read it. This is just the previous statement that we had before. What's important is the moreover. The moreover is the following. It says, if you are almost as stable as the half space or as the majority function, your stability is more than the majority of half space minus epsilon, then there exists a weighted majority function h such that the probability that your function is different than this weighted majority is less than epsilon to some power. Okay?
Just for specific.
For every, what do you mean for?
The assumption is for some O you have this inequality, this you get it.
Right, so if for some O you have some positive O between 0 and 1, you have this inequality. The conclusion from that is your set, and your set is low influences. The conclusion is that actually your set is very close to low influence half space.
Which also means that for every row.
It also means that for every row and so on and so forth. Right? So that's what it says. Okay, so I'll let you look at it and decipher it. Good. Questions? Okay, so the most interesting story, which is, I mean, maybe because it has pictures, and maybe because we don't know what the answers is what happens with pluralities. So pluralities is a much more open at this point, and like I said, you can draw pictures, and by this invariance principle, which I didn't talk about, I did not. Okay, and I don't want to talk about it. Instead, I'm going to talk about partitions of Rn. So the invariance principle, which I also didn't talk about, lets you translate questions about plurality to questions about partitions of Rn and the Gaussian measure, and that's what I'm going to talk about from now on. So believe me that the question that I ask is the question about plurality. Okay, and this is not hard. Okay, so let me repeat what we know in the Gaussian space. I repeat this result by Borell.
Majority is like partition to 2 parts, and plurality is like partition to 5 parts.
Very good. So majority is partitioned to two parts, and plurality is related to partition to more than two parts, right? So the result of Borell that we mentioned before, so if you partition Rn into two parts, then the stability is maximized by a half space, and therefore you get this beautiful expression. I mean, there's a different normalization, because now I guess it's 0, 1 instead of 1 minus 1, but you get a beautiful expression like before, and equality is attained if you partition for half spaces, and is a generalization of the isoperimetric problem. So what we need to know in order to understand what happens to plurality, we need the following theorem, which does not exist. For a partition of Rn into three parts of equal measure, something, okay? So we don't know what this thing is, right? So what is the best partition of Rn into three parts, maybe of equal part, such that you maximize the probability that if I choose my x and my y, they land in the same part. Okay, so we don't know what it is. So I'll tell you about a conjecture. So I think I made this conjecture, and you can see it because I don't have a very visual good field. So people tell me this does not look like the p sign. So but the p sign is actually, it's not 2 pi over 3 in all of them, but I call this a p sign. So this is the p sign conjecture. And the p sign conjecture says that the optimal partition is this partition, right? So this is the origin over there in the center, and you have these slices. Each of them is of 2 pi over 3, and that's the optimal partition. And what if this conjecture is true? It will tell you, like majority is stablest, when you look at function from 3 to the n to 3, the optimal function with low influence is going to be plurality. This is equivalent, okay? So if this is true, that is true.
This conjecture was made in Berkeley?
So this conjecture, I think what happened, if I remember correctly, I made this conjecture, Krzysztof Oleszkiewicz bet against me, and Ryan was undecided, okay? And I think that was the bet, and I'll tell you the outcome in a bit. Or what we know about that.
So the dimension is n, but we just use 2 dimensions.
Very good. It's a two-dimensional phenomena. I just added this line, right? So you know, no matter how large the dimension, as long as it's bigger than 2, the answer is going to be two-dimensional. Like when we had it partitioned to 2 parts, no matter how the dimension was, how high the dimension was, the answer is one-dimensional. Now when you need 3 parts, the answer is going to be two-dimensional, no matter how large the dimension is. So this we also don't know if the answers to this is true or false so far. So. And there's a generalization of that if you partition to k equal measures, the optimal partitions occurs in Rk, R to the k minus 1, and it looks like the multidimensional p sign, whatever this is. So you can guess what it is, and that would be the conjecture. In mass, exactly. Okay, so I'm going to tell you. So the goal of the main slide is the next slide is to tell you for Borel result, the partition in 2 parts. We have many proofs, and we try all of these proofs to prove this partition into 3 parts, and they all failed. Okay, and they all use completely different techniques: symmetrization, a geometric technique, reduction from the spherical case. We have spherical rearrangement. You can do stuff over there. Kindler and O'Donnell have a special case where we use polar coordinates. There's a semi-group technique that was invented in France to do a lot of beautiful things. You can do induction on dimension, which if we skip lunch, I'll show you the proof. You can do stochastic algebra. You can do many things. We try all of them. They don't give anything for this proof. Okay, so that's where we are. And just to give you a little bit more geometric intuition before I tell you what we know, so the geometric intuition here is the following. So the result about partition into 2 parts is the analog. It's related to the following classical isoperimetric result, that the shape enclosing a certain volume with minimal surface area is the sphere. You know, this picture on the sphere. And the picture about partition into 3 parts in Gaussian space is related to this double bubble conjecture or double bubble theorem, that in the case of 2 bodies, what you get is a double bubble. So this is some physical manifestation of the double bubble. You have a little big bubble here and a small bubble here, and you should think about the third body as the rest of the space. Okay, so there are analogs here. If you are a geometer, you can see why all of these things related. If you are not a geometer, it might be harder to see, but you know, there's some same geometric picture that arise in all of them. Okay, so here is what we actually know. So first of all, I should tell you that there are some very exciting new results by Millman and by Immanuel Millman and Niemann, which show that for the isoperimetric problem, which I didn't talk about, I talk about noise stability, but like the noise stability question, there's the isoperimetric problem. Isoperimetric problem, the way to think about it is the correlation goes very, very close to 1. You can still ask what's the probability that x is in A and y is in A as rho goes to 1. This is the isoperimetric problem. So now we have the answer to this question. And the answer to this question is that the p sign is 2. So the shifted y minimizes the Gaussian surface area. Shifted y is the same as the p sign. And similar result for larger Q. This is very, very exciting. There was a partial result by Corneli et al. From about 10 years ago. But Millman and Niemann actually just nailed it for all dimensions. They did it very, very nicely. Unfortunately, a couple of years before, we proved that the shifted y in Gaussian space are not the most noise stable. Okay, so my conjecture, which is the p-sign conjecture, which doesn't even look like a p-sign, is also false in some sense. And what the result is that we know is the following. If you have a partition of Rn to 3 parts, if it's the case that not all 3 parts are exactly 1/3, 1/3, 1/3, that the maximize of the noise stability is not a shifted y. It doesn't look like a p-sign. It doesn't look like a shifted p-sign. And in fact, it cannot be flat. It cannot be that all parts of the partition are hyperplanes. It has to have curvature. Okay, so this is a mystery. We really don't understand what's happening here. There are a lot of signs telling you that something like the p-sign or the shifted y should be the answer. On the other hand, we have a proof that this is not the answer. Okay, so that's somehow where we stand right now. Okay, so say again?
How you prove it? Like what's in the...
What's in the top theorem or the bottom theorem? Say again?
In the bottom theorem.
So the bottom theorem uses something that you cannot use for isoperimetric, for the surface area problem. We use ideas from complex analysis. Somehow noise stability is a smoother thing than surface area. Surface area is sort of a very, when you move stuff around, you feel it. In noise stability, when you move stuff around, it's things, because of the global effect of the noise stability, that every point can be connected to any other point with some probability, things are much smoother. Which lets you use ideas from complex analysis. It lets you use the fact that some function is analytic, right? And then you can use some complex analysis. And it's clear that you cannot use these ideas at all in the isoperimetric area. The result is essentially the following. I look at the proof goes the following. You look at the y, and you say, I'm going to prove that it's not optimal. How am I going to prove that it's not optimal? I'm going to construct a function that will show that if I move things a little bit, I will get better. How will I prove that it will get better? I will use the fact that this function is actually analytic, and therefore I can say some things. Okay, so that's somehow the basis of the proof.
So it's not even a local. The shifted y is not a local.
It's not even a local. Right? So we prove that exactly. It's a variational argument that shows that it's not even local. Good. Okay. So this is a shifted y. Now it's called a shifted simplex. P sign, simplex, and y, they're all the same. So maybe I'll conclude here. I think this is very, and maybe I'll just mention a few more open problems so we don't, not too late for lunch. So the balance case, so the case of noise stability, where we have 1/3, 1/3, 1/3, we still don't know what the answer is. There's a result of Steve Hellman from a couple of years ago that shows that standard simplexes are more stable in Rn if the dimension is low enough as a function of rho. And rho is close enough to 0. Okay, so we really don't understand what's happening here. We have no techniques, no intuition, no guesses. We're completely lost, right? So that's what I wanted to tell you about this part. Okay, so let me mention.
This is fairly strong result of the
Yeah, but this result, sorry, I should only hold for rho that's small enough. So there's like, if rho is less than 1/billion, and in small enough dimension, then you get that this is the most stable partition. Okay, let me mention some other open problems. There was a conjecture that majority is the least. Now I'm going to confuse all of you before lunch. There was a conjecture that majority is the least stable function, but the least stable functions among all majority functions. Okay? So you can look at all majority functions. And you can look at all weighted majority functions. You can look at the simple majority, and you can ask, is simple majority the least stable among all weighted majority functions? This was conjectured for I don't know how many years ago. It's not exactly true. There's some counterexample. I think the first counterexample is by Gopi from about 4 or 5 years ago. But maybe in some asymptotic sense, majority is the least stable, so that's a natural open problem. It won't have a huge ramification, but I think it's interesting. Something that came up to me only when I prepared this talk, which I feel embarrassed about, is that let's look at maybe fq to the n to q, not to 0, 1. Let's look at f from q to the n to q. Is it true that it's noise stable if and only if a random restriction of the function is correlated with a plurality? Like the majorities, or do we have such result for pluralities? And again, for other domains, that's an interesting question. Okay, so I won't torture you through a proof. I won't give you a sketch of the proof of the majority of Stablest. So I'll stop here. Thank you.